Falling objects with air resistance. The kinematics unit covered objects in free fall, and we only had gravitational force acting on the objects. They fell with a constant acceleration, and the velocity increased as a linear function of time or as the square root of the distance fallen. Near the surface of the Earth, there is an opposing force to gravity for falling objects, the air. Air is a fluid, and it provides a resistance force, which is also called drag, that opposes the object's downward motion. This force typically increases as a factor of the object's velocity squared. At the point where this force equals a gravitational force, the net force is zero, and the object will fall with a constant velocity, and another name for that is terminal velocity. The resistance force can also be increased by increasing the surface area of the object falling. This is a great demonstration in class, where you take a piece of notebook paper and drop it. It falls very slowly, but then when you crumple it up, it falls very quickly. This is part of the theory behind parachutes, which reduce the terminal velocity of the parachutist, which is a very good thing. Let's start with Newton's second law for an object with terminal velocity. That means we want to find, at the end, the acceleration is equal to zero. So we have the sum of the forces is mg minus k vt squared equals 0. Terminal velocity will then be the square root of mg over k. What we're doing now, here's our forces on the object that's falling. Here's the friction force in the up direction, and here's mg in the down direction, and we will take the down direction as positive here. A more interesting problem is finding the velocity at any point as the object falls. This will require the use of integral calculus, specifically the techniques of separation of variables and change of variables. We're also going to change the frictional force to a linear dependence on velocity. So the friction force will equal minus kv instead of minus kv squared. The reason we do that is the integration is simpler. So once again, we start with Newton's second law, and in this case, instead of equal 0 to find the terminal velocity, we're just going to set it equal to ma because we want to find the velocity at any point in time. Same free body diagram, except here we have kv, not kv squared. We then replace a with dv dt, and we have a differential equation here. And the way we solve that is by separation of variables. We'll put all the terms on the left side that have something to do with velocity. So that's dv here and kv here. And the right side, everything that has to do with time, and that's just dt. The next thing we do, we want to integrate that to some future time t. So we go from 0 to t. And our initial velocity is 0. And then our velocity we want to find at some other time, which will be v. We repeat from the previous slide. Here's our integral. And that looks a little confusing, and that's why we do change of variables. We're going to let u equal mg minus kv. That's our denominator term here. Well, if we do that, we also have to change dv. So we take the differential of both sides, and we find du is equal to minus kdv. Mg is a constant, so that drops out. So dv is du over minus k. We substitute those values back into this equation here inside the box. We get this. And then we multiply through by negative k just to clean up the integral on the left-hand side. So we now have the integral from 0 to v of du over u minus km, the integral from 0 to t over dt. Not terribly mathematically rigorous here. We should have also changed the limits of integration for u because we're dealing with an integral with u now. But you know what? We'll fix that later on with a shortcut. Here's our integral from the previous page. And if you'd like, go back a page and see what would have happened if the friction force was kv squared. That integral would have required a table of integrals to solve, or solve it by trigonometric substitution, which actually is pretty cool. So if you've done that in math class, go ahead and go back and do that solution. But for this one, we're integrating du over u, which is ln of u, and we have to evaluate it between 0 and v, which we can't, right? That's That would be if we had integrated with respect to v. So what do? Let's just put v back, right? Where u is equal to mg minus kv, and then we can use the original limits of integration. That's that shortcut I talked about. So here's what we have now by substituting in u equals mg minus kv. We evaluate the right side, and that's just going to be k over m times t. The left side will be the ln of mg minus kv minus the ln of mg. We then use the property of logarithms here to put that into a fraction. And now we have ln of mg minus kv over mg equals minus k over mt. And we'll take the exponential of each side. Well, that clears out the ln on the left side and raises, we have now minus k over mt, and that's e to the minus k over mt. Now we're just going to use some algebra and just keep going down from the top until we get to this point here, where v is equal to mg over k times 1 minus e to the minus k over mt. So let's look at that term over there that we just pointed to. If we wanted to calculate the terminal velocity for this linear frictional force, or drag, we would sum up the forces, which is kvt minus mg equals 0. Because when acceleration is equal to 0, you have your terminal velocity. We find that the terminal velocity is mg over k, which is this term here. So we can rewrite this now for our final answer as this. And now let's check limiting cases. What happens as t approaches infinity? Well, what's going to happen then is this term here will cancel out, and we'll have v is equal to v terminal. That's good. And let's take for time equal to 0. Then we're going to have 1 minus 1 is 0. The velocity will be 0, which is good. That's our starting point. So the limiting cases bear this out. Let's further analyze what's going on now that we have this expression for the velocity. First thing we'll do is just graph it. Notice how the velocity increases with time and then asymptotically approaches the terminal velocity v sub t. And you can use this with the graphing calculator or any popular graphing software. To find the acceleration, we need to take the first time derivative of velocity over here. So there's our velocity that we've calculated. Acceleration is d by dt of the velocity. We calculate that out, and we find that the acceleration is ge to the minus k over mt. Now that's an exponential decrease, and when you plot it, you see that we start at g. So when the object first falls, before the acceleration kicks in, you have a 0 velocity, so you have the maximum acceleration there, which is g. Immediately the friction starts coming in, and it decreases your g until eventually, well, it doesn't decrease g, it decreases your acceleration until it's equal to 0, and that point will be where v is equal to v terminal. For the position, we need to integrate the velocity. So once again, here's our velocity. We're going to integrate it with respect to time to find our change in position from 0 to t, and we carry out the integral, and you can see where you integral 1 dt, you get t. You integrate e to the minus k over m t, and you get plus m over k, right? Because this negative here will cancel this out. E to the minus k over mt. We evaluate that between t is equal to t and 0, and do a little algebra and come up with this expression here. So on the next page we'll talk about that, but if you were to go ahead and plot that right now, you would find out that you have this exponential decrease in height. Then at the point where v is equal to vt, we have a linear decrease. And why would that be? Well, that's where you have your acceleration equal to 0. So if you wanted to sketch this graph on your own, just looking at the mathematics here, at the equation, at time is equal to 0, delta y is 0. It has not yet begun to move. So you're up here. You have no change. Then when you do start moving, the exponential part of the equation will dominate when t is small, which explains why we have the exponential decrease here. As t increases, This term here is going to approach 0, and your displacement now will be linear. It will just be this term right here, the v times t, and that's why you get the linear portion of this equation.